Okay.
Perfect. Okay.
Okay. Sorry, I was trying. Okay, cool.
Okay, let's let everyone in.
Yeah, sounds good. Thank you.
All right, can we get started? Perfect. Hey everyone, thanks for joining us this evening. Welcome to the Backend study group series with Women Who Code. We have changed a few things with the format of the session. So before we jump into the session, I'd like to talk about that. So starting today, we are again going to start recording the session. So the recording would be available once the session is over or in the next few days. And then by default, everyone would be muted throughout the session. And if you have any questions, feel free to post them in the chat at any point and I'll bubble it up to the presenter. And if you want to like verbally ask the question, we'll save a few minutes at the end. At that point, you can raise your hand. I'll unmute you and then you can ask those questions. Yeah, pretty much that's it. Prachi, can you go to the next slide? Perfect. Yeah, so welcome everyone once again. My name is Harni Rajendran. I'll be hosting the session today. I've been volunteering with Women Who Code for over a year now. I'm one of the leads of the San Francisco chapter, and I work as a software engineer with a company called Confluent. And today's presenter is Prachi. She's going to talk about database designs. And yeah, I'll let Prachi take it up from here.
Yeah, thank you, Harini. Welcome everyone. Those of you who are new, we are a backend study group at Women Who Code, where we talk about everything computer science and backend engineering. And today's session is going to be about database design, where we will understand, what is a database, what are relational, non-relational databases, and then we'll go over some of the design practices and data modeling, and then a really small, quick demo of, basically relational database and query. A little bit about me. I'm a senior software engineer at Tapjoy and a director at Women Who Code San Francisco. Quickly go through like what backend engineering is. Backend is everything that a customer or front end doesn't see. So it's in backend engineering, we design, build, and maintain server-side web applications. Some of the common terms from the backend side are client-server architecture, networking, APIs, web frameworks, all sorts of platforms, microservices, databases. All these things are considered a backend side, and a backend engineer is aware of these terms, and this is a core requirement or core knowledge, even on the computer science side, that entails backend engineering. When it comes to tech stack, some of the backend languages or frameworks would be like Java, PHP, .NET, Ruby, Python, REST APIs, AWS stack, Node.js, SQL, NoSQL, etc. Some of the other domains within computer science or subdomains within computer science that align with the backend engineering would be front-end engineering, full stack, design, user experience, mobile development, DevOps, machine learning, etc. So we'll quickly start. So database is basically a collection of organized data, right? All you want to do is you want to store some data, you want to retrieve or read, and you want to manage or manipulate data. In a database, you store, basically databases support different data types and formats. It can be as simple as, like text data, or in text data, it can be a string or a number, and it can also be like files and objects and stuff like that, which we'll go through. Some of the tools or databases available in the market are like, MySQL for relational data, OracleDB, MongoDB for NoSQL data, DynamoDB, Redis, which is a key value store, etc. Databases support features such as data redundancy, backup, replication, querying, and scalability. Some of the different types of databases are like, some kind of centralized database. You also have distributed database systems, NoSQL database, SQL or relational database, cloud databases, network databases, object-oriented and hierarchical. So there are all different kinds of database types, and depending on the data or business case, you can categorize what database you are choosing. So we'll go through relational database first. There are two major types of databases that we're going to cover today. One is relational and the other is non-relational. So relational database is a collection of one or more tables. Data is stored in a tabular format. So you have rows and columns. And these tables have relationships between them. So that's why it's a relational database. It's optimal, these kind of databases are optimal to store like some kind of structured data, which has some meaning to it. And we use structured query language to write and query data. So to write, read, manipulate data, we use a structured query language. Relational databases are typically ACID properties compliant, which we'll go through in a bit. And the way we manipulate data, or we read data, all these kind of queries or statements are called transactions basically. So in a relational database, you have certain set of commands to read, write, or manage your data, and these commands are called transactions. So you are doing data transactions on a relational database. Relational databases are ideal for like banking transactions, insurance data, wealth management data. Primarily, all of fintech or insurtech or insurance technology is primarily relational data, because there's a lot of data that is captured, and this kind of data has some meaning, right? So like I can give an example. If you are a customer at Chase Bank, right, you may have some kind of account information, you may have some kind of profile information, you may have some kind of your payments, credit card bills, right? You might also be enrolled in some kind of investment instrument with the bank. So all of this different data related to you as a customer is stored usually in relational data, because there is some link between this kind of structured data. So fintech primarily is a great example of relational databases. Some of the very common relational databases that we know of are like MySQL, PostgreSQL, or OracleDB, and you can decide. All these are relational, but you as a company or even individual can decide what database you want to choose. And it can be things like how much data a particular database supports, how can you scale it, how does indexing work, how fast is querying. All of these things you need to consider and compare before choosing one particular software or tool or database type. To the right, you can see like an example of a relational database where you have different tables here, and there are rows and columns, and this data is related, right? So a student can enroll in courses, and you have basically documented here what course the student is taking. So all this data is linked. There are three different tables, but they are linked. So it's structured data and it's related. And that's how you typically store structured data in a relational database. And also some examples of popular relational database softwares out there. Yeah, so something we have to understand when it comes to relational databases is ACID properties. All relational databases or SQL databases are ACID compliant. And, what that means is that, there are four properties here. The first one is atomicity, which means that any data modifications done per transaction is a single operation completed successfully or fails. So let's say if you are updating a database, a table or a record, right? And if it should be considered a single operation, complete in itself, and it should either successfully complete, and if it's not able to for whatever reason, then it should completely fail. It should not be left midway where we don't know what the status of the data is or the status of the database is. So one transaction, one command, or one kind of modification on the data is considered one single operation, and it should either completely be successful or it should just fail. So that's atomicity. The other property is consistency. So data is in valid and correct state after the end of transaction. So if you have atomicity property, right, your transaction completes, and that renders your data or your database system in a valid and correct state. You should not make incorrect modifications to the data, or non-compliant changes to your data or your database. So your data and your database should always be in a valid and correct state after the transaction or any kind of data modification that has happened. Isolation is multiple transactions executed in isolation. So, there's some form of parallelism here where on the same set of data and on the same database instance, you can keep on having multiple data modifications or transactions, and they all work basically isolated. And even after all this, your data and your database is still in valid, consistent, and correct state. Durability. Data modifications are permanent after a successful execution of transactions. So once you have modified your data, those modifications are considered permanent until there is another update to that particular set of data in this example. So any modifications after a transaction is successfully committed or completed is considered permanent. So all relational databases are ACID properties compliant, and some of these things are, if you choose Postgres or if you choose MySQL or Oracle DB, some of these things are, out of box provided, and other things you as a developer or this database designer would want to do this. So things to keep in mind when designing a database. Some of the very common operations that we do with relational databases is, you create tables, you drop tables, which means in theory delete the table, and then you can alter a table to modify the structure of the table. Other common operations are on a particular row or column. You can basically columns or record. You can insert new data, you can update an existing data, and you can delete a particular record or a data point from the table. Some other operations are related to permissions, where your database can have all sorts of different users, and you can grant permissions to this user, grant all sorts of permissions to a user. For example, I can only read from a database, whereas Hardini can read and write and execute queries, right? So stuff like that. So you can grant permissions to users, and you can revoke permissions from them. Some other common operations would be, after a set of commands that you run, you can commit all those commands, you can roll back previous commands, and you can, save transactions, which means you save the data permanently. And the select query, which we have, which is for querying / reading the data from the database. Yeah, here is an example of some of the queries that we have on a typical relational database. So here you can see I have a student management service, and I have my database table named student, and this is some information that I'm persisting, right? The student ID, advisor's name, date of birth, their degree, their enrollment status, first name, last name, year of enrollment, etc. And some of the commands that I would run, SQL commands that I would run on this kind of data this kind of table would be, first I'll start with creating a table. So I'll create a student table with the first name as my column name, and the data type, which is varchar, and I'm only limiting the first name to 50 characters, right? And then I have a last name, let's say I'm limiting it to 50 characters, and then date of birth, which is of type date, and student ID, which is an integer. Right? So I'm creating a table. Then if I want to drop this table or delete this table, I will use the drop table student command. If I want to alter this table, then I'll alter the table, mention the table name, and add a new column, which is the degree. And I'm limiting that its size to, a varchar, which is string, and limit to size 100. Right? And then, so if you limit the size of, one thing to notice, if you limit the size of your column at the database level, then the software itself will restrict you. Like if you try to now store a name of a degree which is 101 characters, the data modification will fail at the database level because you have that constraint added already. Another example would be update a column. So I want to update the student table and I want to change the first name to John, where the student ID is 3. So the student ID with like value 3, I want to update their name to John for some reason, right? So you can always update very specific columns or values, in your database. And I use the select query to select or read or show all the students in my student table. So these are some of the very simple queries you can do on a relational SQL database. And structured query language have all sorts of commands, and there is a proper format of how you can write queries on your relational database. Now we'll look into like non-relational databases. So non-relational databases are very different. They are the data is basically persisted in a non-tabular format. So like relational databases is clearly row and columns, and a row column combination is the record, right? And data is structured and your data is related. But non-relational databases, you persist data in non-tabular, non-row column. Traditional row column format is not what non-relation data looks like. NoSQL basically stands for not only SQL. It's not the best name, but people wanted to come up with something that is not very traditional row column structure, and people came up with the term NoSQL. Some of the examples of the data, the kind of data that non-relational databases persist is, you can store an entire document. You can store some kind of like, key value pairs. You can store graphs. Graphs usually have nodes and edges. So these are some of the examples of, your non-relational NoSQL data. Understand that data model varies per database, with a relational database and with SQL, you can choose MySQL or Postgres. Your data model is the same, right? It's some kind of row column structure and data is related, right? But depending on the kind of NoSQL database you select, your data model will be either a document or a key value pair or a graph. So it can completely change, and therefore design or your modeling can also change. NoSQL databases are ideal for big data sets because you can determine the kind of data structure you want, like graph or document or key value. And these databases are typically designed to solve the problems that a traditional SQL relational database is not able to address. So they're designed for scale, they're designed for distributed systems, they are designed for big data sets, and they're designed for non-structured, to persist non-structured data. We looked into how relational databases are ACID compliant. For non-relational databases, we have to look into a different standard, which is base properties compliant. And what that means is that your data in a NoSQL database is basically available. So, data is available as per CAP theorem, which I'm going to talk about. Your data is either consistent across system, or it's almost available, but not up to date. Let me step back and quickly now talk about CAP theorem. CAP theorem is something that applies to data and data persistence and how any kind of database is designed really. CAP theorem stands for consistency, availability, and partition tolerance. And for any kind of data, only 2 of these properties are applicable at a time. So your data can be either consistent and available, it can be available and partition tolerant, or it can be consistent and partition tolerant. And what this means is that if I think about consistency, right? My data is consistent across systems. So I can have 4 different databases and 5 different instances for each of the database, but my data is the same and consistent across all these systems that I have, right? So it's the same. It's not like one database is different value compared to the different instance of the same database. Then your data is availability, right? So your data is available, but not most updated at a given time. So let's say you write something, onto a system, and it's started to persist through your system, right? So you have 4 databases. It has to persist on all 4 databases. So it's wrote to database 1, it wrote to database 2. It hasn't wrote or updated that data in database 3 and 4. So if you read from database 3 and 4, you might not get the most updated information. So availability takes time, but like, you know, you have to understand that your data might not be the most up-to-date and therefore up-to-date information, up-to-date data available at a given time. Eventually it will. And then partition tolerances, despite of network failure, system failures, your data is still persisted, modifications are permanent, and you are able to read, you know, you are able to fetch updated most updated information. So that's something, these are some of the challenges of data persistence and all databases that we have. And you can only achieve 2 of these properties at a given time. So if I think about base properties compliance, your data is basically available as per the CAP theorem. So the idea is that, you know, like you are getting the most up-to-date information that is there, that is persisted in your systems. The other, that's basically available. Soft state is, you know, like data may change without new inputs or updates. And what this means is that, you know, it's not necessarily a user action that causes any change to, you know, like your database. There can be other systems that in the background that are, you know, linked to your database, and, you know, some background job or some process that's happening that might be updating your data, right? So data may change without necessarily new input or updates from a user. And then eventual consistency. What that means is that data will be consistent over time with multiple copies of data for high availability and scalability. So, you know, eventually all your data systems will be updated with the correct, most up-to-date information. But there are certain databases or instances of databases available just to ensure availability and scalability. So and these are some of the things that you get off the bat when you use NoSQL databases, and some of the things to also consider when you are understanding your business requirements and doing data modeling. You know, why would you want to choose a document store compared to a key value pair database or compared to graphs, right? So you have to keep understand these things in mind, and depending on what data structure you choose and what tools you have, you can look into how these things are implemented, right, per database or per software, and then you can make a decision as to what NoSQL software do you want to use and why, or what are your trade-offs, right? Do you want to optimize for most up-to-date data, or do you want to optimize for, you know, eventually my data will be persisted properly in all systems, and that's okay. I don't want to get the most up-to-date data all the time, right? Do you want to optimize for consistency and availability, or partition tolerance and availability, or consistency and partition tolerance? So you have to understand what you're optimizing for and what are the trade-offs, and then decide what NoSQL software you want and how you want to do your data modeling.
Prachi, there are a couple questions in the chat.
Yeah, we can, I'm taking a look. Non-relational databases are best used for large amounts of data storage versus relationally best for smaller amounts of data. It depends. No, that would be second consideration. I think you want to decide between SQL and NoSQL depending on what kind of structure your data has, and what is the relationship between data, right? So that's the first consideration. And you can always you know, pay more for different kinds of softwares and do migrations, and you know, continue to have a relational database, because it depends on the kind of data you have. So if your data is relational, go for a relational database. And there are softwares like MySQL and PostgreSQL don't scale much, but you can always use an AWS relational database, right? And they don't have limits to their scale. So it takes care of large data sets, large relational databases or data. So it's fine. So consideration should be more about, like, is it structured versus non-structured data, or how do you want to persist your data? And there are different softwares which are SQL and non-relational SQL, which more like relational databases, they limit. They have certain limitations on the scale, but if you use something that's you know, provided by AWS or Google, these are all they persist data on the cloud, and therefore there is no, in theory, well, in practice, more like no limit to how much you can scale. And scalability means how large amounts of databases are efficiently handled. There are different things. Scalability here means the amount of data you can store, petabytes and stuff like that, but it also means, then there are other things to keep in mind, how available the data is, how fast you can read data, how performant your queries are and stuff like that. And all of this you can look into as you decide what software you want to use. Captain is used to choose between different types of databases. Read heavy or write heavy databases. Yeah, so like I said, right, you want to, we'll look into that as we compare SQL and NoSQL but in the upcoming slide. But yeah, if your data is more read heavy, you might want to design it in a certain way, choose either relational or non-relational databases. You want to design how your system should be, how you want to scale them and stuff like that. So you have to understand all of that as you decide what kind of database you want, what software you want, what are your trade-offs. I think I answered everything. I'll just continue. So yeah, non-relational databases are primarily of 4 types. The first one is like your key value pair. So data is stored, the core data structure is your hash table, and you have a key, a unique key, which is in comparison to your primary key in a typical relational database, but you have a unique key, and your value is either a JSON file or some kind of JSON structured data, or a blob, or some kind of string value, right? So that's your value format can change, and you have a typical, you have your unique key, which is usually a string or some kind of number. So it's a key value. So if you look, yeah, if you are familiar with the concept of like hash tables, you understand what key value is. It's a core data structure. It's a schema-less data structure because, you know, like key value, you have a key value, which is fine, but your value data type can change, right? Like it can be JSON, it can be arrays, it can be dictionaries, you know, your blob. So you don't necessarily have a specific kind of schema in comparison to a relational database, right? Where your schema is defined, it's row and column, right? So here, that's not the case. Some of the very common key value pair NoSQL databases are Redis, DynamoDB, Memcached. Usually key value databases are used for caching. So you want to store some very quick, short information, you know, that can be cached and quickly read. So Redis and Memcached are ideal databases for caching. That's the majority use case. Column-wide databases are data stored in like contiguous large columns. If you see on the right, the first diagram, it's a column family. That's how this is structured. So this is slightly different from your very traditional row column database, where you have different columns that persist, contiguous large columns that persist a lot of data, and you know, these are like called column families. This kind of database is basically optimized for storing business intelligence and data warehousing kind of needs, and these are designed for for querying. So they are optimized for better, improved performance for querying. So if you have data which is more read heavy, then and it's not necessarily super structured, you don't need to have a rigid schema like what we have with, like, let's say your typical relational database. Then you can consider, you know, Cassandra or HBase, which gives you a little bit a different version of a traditional row column structure. You have column families, but it's really super optimized for one purpose, which is like, you know, high performant queries. And that's your trade-off. That's when you want to choose something like you want to choose a data structure which is column wide, and you want to choose, let's say, Cassandra or HBase, right? Because you're optimizing for read heavy data, which is, and therefore you want your queries to be super efficient. Another type of NoSQL data bases like graph-based, where, you know, you have a typical graph structure, right? You have nodes and edges, right? Edges connect the nodes, and your data entities basically, or data points, are stored as nodes, and the relationship between these edges, between these nodes are called edges, right? These kind of database is ideal for like, your social networks, your spatial data or logistics, right? Because you have like, you have multiple relationships between different data points. And if you look at the diagram to the right, like we have 3 nodes, person, city, restaurant, and each edge has defines a different relationship between all these entities, right? So graph-based database, or this graph data structure is best for such a use case. Some of the common tools or softwares are like OrientDB or New, which are graph-based databases. And the fourth one is the document store, where it's like a extended version of a key value pair, but like your key would be some kind of unique key, a string or integer, whatever you want to choose, but your value is an entire document. So it can be some JSON file format, it can be XML file, it can even be images. So it's a complete document in itself, which is your value, and you're storing an entire document in your database. It's not a typical row value data. It's ideal for low querying data, for and it's ideal for like blogging platforms or CMS applications. You have an entire document, you don't want to read every line of the document to find what is going on. So these kind of database is perfect for like write heavy systems, where you're just writing things, you're not reading much, and even if you're reading, then it's you can afford to have like the performance of querying can be low. It doesn't have to be the best because it's write heavy. Like a blogging platform, you write a lot more than necessarily what people read, right? So like reading can be slow, it can be the low performance queries, but you're optimizing for I can have any kind of document, and the document format will change, but my database supports that. I don't necessarily want to break a blog into row and column kind of data structure. I want to store the entire blog in itself, right? So store it as a document, and your document store is what you want to choose as a database or type, right? So some of the examples of such databases is SimpleDB or CouchDB or MongoDB. They persist documents, and then you can decide between the 3. Like what do you want to optimize for? What are your trade-offs? How scalable these softwares are, and then you can determine what you want to actually use. Relational versus non-relational databases. So here, like it's just a graphical representation. Your structured query is row, columns, tables, and they are related, right? There's some kind of relation. Your document store is just a hierarchical structure of all the documents you have. Graph-based databases are, nodes and edges, and they have also some relationships between them, multiple relationships. And your key value store is every unique key has some kind of value, and this is how your data looks like. And column-wide is you have like large columns, and they are in continuous. They are column families, so contiguous large columns is how you want to process your data. If I have to compare relational and non-relational databases, relational databases are strictly ACID compliant, whereas non-relational databases can be somewhat ACID compliant, but they would sacrifice that over scalability and eventual consistency. So with NoSQL databases, you are optimizing for scale, so big data or large data sets, and your data will be eventually consistent. So that is what you want to optimize for, rather than the state of the data is like, ACID compliant at all times. That's not a requirement. That's not what you are optimizing for. So that's a trade-off. Also, SQL or relational data is optimized for efficient data querying, right? Because you have your row and columns, and when you query or you modify, you are modifying you're modifying different data points. So these kind of systems are optimized for efficient data querying. With non-relational databases, also depending on the type of data structure or database you have selected, querying is limited. It's not the most performant, and again, depends on the database you choose, but not all NoSQL databases will be optimized for querying. That is not the case. They are optimized for high availability or scale or eventual consistency and stuff like that. So that's something to keep in mind. If you're considering, hey, I have banking transaction or payment information, right? Should I choose relational database or non-relational database? Well, what are you optimizing for? And that's something you have to keep in mind. Like I said, relational databases support structured data models, whereas non-relational databases support structured, semi-structured, and unstructured data models. So that's a big benefit. Your data can be of any kind, depending on a business use case, and you can persist it as you want to. Relational databases have rows and columns data structure, right? So the schema is rigid. The data model is only of one type, and any kind of data you want to store, if you're choosing relational database, it has to be in the form of rows and columns, and the kind of relationships you define and the kind of constraints you define is somewhat like it's standardized. With non-relational databases, you have all these different kinds of data structures you can choose, and the relationships you have between all different kinds of data points is unlimited. It's not structured, or it's not completely standardized. There's not one way to do something. Design practices. So when you look, now that we understand the different kinds of databases and softwares and what are the limitations and constraints, we have to, as a software engineer, if you don't have a DBA team at your company, you will end up doing the database design. There are some of the things you have to keep in mind while you understand what data you're dealing with, how you want to design your models, how you want to persist them, how you want to maintain them. And if your data, assuming your data grows with time, what kind of challenges would you have and how to go about it, right? So you have to think about like at least 3 to 5 years down the line as you design your data models today. So some of the things to anything with design in general, like try to keep it simple, right? Try to keep it intuitive. Maybe start small, right? Like keep it simple, easy to understand, and keep it intuitive. And then you can build on top of it as you want to scale, as you have more and more complicated business problems to solve. So just start with keeping it simple, keep the design intuitive, easy to understand. And then as you work on complicated problems, you keep the understand that if you design your database today and your data models today, after a few years, things will look different. You'll have more data, you have more different kinds of data, your business needs will change. So always consider future modifications in time. Also, safely assume your data volume will grow over time. So like what are some of the things you can do today to make sure that your data volume will grow over time. There might be future modifications to your data. How would you go about doing that, right? Can you assume certain things, predict certain things, and accommodate those challenges in your design today? So always consider future modifications and make some certain assumptions and keep that in mind while you are doing data modeling or you're designing a data system, right? Choose the correct software for the data type and business needs. You always have to understand your business needs and your product needs, and then decide you want a NoSQL database or a SQL database is fine, right? If you're choosing NoSQL, then what is your core data structure? Should be graph based or should be column wide? If column wide, then do I need H base? Do I need Cassandra? Edge base might not be optimized for high performance querying, but Cassandra is. So is Cassandra better for me? Is it read heavy? Does query performance matter to me? Fine, then I'll choose Cassandra. But Cassandra is costlier than HBase. So then do I want to spend money on something very expensive right now, or I can address the problem of cost 3 years down the line when my data volume grows? So I want something that's cheap, bare minimum, does the job. So some of the things, all these things you have to keep in mind as you determine what software you want to use, what data type you want to use, what are your data needs, business needs, and how they'll grow over time. Always optimize for reducing data redundancy. This is a problem with, typically a problem with structured data, where you're storing the same kind of data in all different tables because there's a common relationship that's there, and you want to, as much as possible in your design, avoid data redundancy, data duplication. So, you're not storing more than what you necessarily need to, because this brings problems of maintenance, scalability, and always cost. Cost is something to always keep in mind. The more redundant data you persist, the more costs will rack up because now your volume is growing over time. accommodate for data analytics and reporting requirements. Now, this is more applicable on the enterprise side, or the corporate side, but it's like usually companies, when they process any kind of data, they always want to store analytics. They always want to get all sorts of reports from the data that they are processing, right? So they can improve upon their features or their business needs, right? So they would want to store something like, okay, hey, what is the location of the user or the IP address, right? Or the timestamp. They would want to store all this other analytics information that may or may not necessarily contribute to their core product, but it helps them with, like analytics, reporting, and all sorts of other very back-end business needs. So if that's something that your company is already doing, maybe accommodate for data analytics and reporting as you design your data models, right? Like make sure you're capturing location information or IP address or something like that. Determine relationships as for business needs. So you have to understand what your business needs are and what your product is and what kind of data you're collecting from users and what is the kind of user and stuff like that. And depending on that, you would want to define a relationship between a student and, relationship between your data, right? So one example would be like you have a student management system. You have information about the student and the advisor or professor and their courses, right? But in this system, you don't need to know about who the university proctor is or other departments or other schools at the university, right? Not necessary. You are only focused on the student information. You don't care about anything else. So then, like your business need is all about managing student information. So that's the relationship you have, and you don't need to know about anything else. So understand your business needs and then understand what your data looks like and what relationship you want to establish between different data points, and then how you want to process this information, right? I already mentioned know when to choose SQL versus NoSQL. We already talked about it. Usually many systems are like read heavy. So you always want to optimize for data querying. So accommodate that in your design and also understand what software you're picking and what does their querying, what are some of the optimizations they provide and how performant systems are. This will be part of the trade-offs. Again, like I mentioned, determine your performance requirements, right? Like you want a database which is best with gives the best, most performant querying, but might not be good at scale or be really expensive. Then what's your trade-off? So always usually optimize for performance because it saves a lot of costs and headaches when it comes to maintenance in the future. But optimize for querying and performance. You have to understand your requirements and then determine, right, what kind of database you want and what software you choose. And understand maintenance challenges, right? Like how does your data look like 3 years down the line, right? Like how much, what software, like if you're choosing a software, let's say PostgreSQL, and if they are having all sorts of maintenance nightmares as a software in itself and there's no community support, then it would be a lot of maintenance nightmare because you as a developer might have to end up solving a lot of these problems. So understand your maintenance challenges within your business, your engineering tools and practices, and how your data is, right? And then if you can understand these things, if you can predict, then maybe accommodate for these things from day one. And leverage data modeling techniques to properly model your data. So we'll now look into some data modeling techniques. What data modeling is basically, once you understand your business needs and what data you want to gather or collect, you would want to kind of model it, right? You would want to come with some schema, some structure, some format of, hey, this is our business, these are our users, these are our features, now this is the kind of data I want to collect, and this is how I'm going to read, write, manipulate my data, right? So data modeling basically means you're organizing your data and you're determining the relationships between the data, right? So you'll define some kind of constraints or rules. You'll select what data type you want. Is it graph? Is it key value? Is it your very traditional row column, right? So you have to make these decisions. And usually, at least at the enterprise level, you want to structure your data as per your current business needs and how things would look in the future, right? So your data looks similar to your business entities or your domain, right? And it aligns with what your business needs are. And like I said, data is modeled after real business or product entities, right? So one example here is, like I have something like, like an Amazon website or e-commerce, right? Like this is how my data looks like in the backend side, right? Like I have a product table, which has a product ID, vendor ID, product name, and some other information. Then I have my customers table, which has some other information about the customers. And then I have my vendors. And then between product and vendor table, in this example, it's a relational database, let's say, I have some relationship between my product and my vendor, right? Like one vendor can produce many products, right? So that is a relationship that, one vendor has at least one or more products that they have manufactured and are selling. So in this example, like product, customer, vendor, all these entities or tables, and the relationship is very closely modeled after like real business problems, right? Or real product problems, or what real product actually, which is e-commerce, right? So your data will look like your data should be modeled after like real business or product entities and relationships. There are 4 ways to do data modeling, and in this order. So you want to start with like conceptual modeling, then you do logical modeling, then physical, and then at the end you have actually created your database. So this is a standardized process. Typically, that's what engineers or DBAs do at companies. So you start with like conceptualizing, right? Like, hey, these are my business requirements, these are my product requirements, and based on that, these are the entities or tables I'm going to come up with, right? Hey, this will be my product table. I'll have a vendor table. Let's have a customer table where we store everything customer related. Okay, so we will conceptualize our data and it will be modeled after our actual business needs, right? So we'll define the entities, we'll define the attributes, which are features of entities, and then we'll determine what data type we want, we'll determine what relationship we want, right? Example was, hey, vendor will manufacture one or more products. So it's a one-to-many relationship in that example. So we just at a very high level, you have our entities, our definitions, relationships, and attributes, right? Then we'll step up. We'll now look into like, the logical design, where we'll apply the business rules. So let's say, a vendor will always have at least one or more products that they are manufactured. It can never be 0, right? That's a business rule. That's what you want to now apply and you want to accommodate, right? So in your relationship, so you're stepping up. So another example would be a product is always manufactured by one vendor, right? It's not possible that a product will not be manufactured by any vendor. There has to be at least one vendor, right? Ideally one vendor. So that's a relationship or constraint or business rule you would want to apply. So now you have to think about all of that. Like, what are your requirements? Are there any business rules you want to consider? And that's what you want to apply to your design next. So you will define constraints and you will improve your relationships, right? Between entities or data points. Then the next level is physical modeling, where you'll think about your performance requirements or more like technical requirements, right? Like you have different columns and tables, let's say in this example, what are the features of the key? What is the primary foreign key? What does that relationship look like, right? Do you want to add indexing? If yes, then on what columns? How many indexes do you want to add? What tables do you want to index? What columns do you want to index, right? Stuff like that, like how performant will your database querying look like? You don't want to index everything that you have persisting. Maybe you want to index very few key things that are mostly read, right? So those kind of things you want to keep in mind. The performance side of things is what you want to keep in mind. So that's the considerations now you have. Technical or more performance requirements. And once you've determined all of this, then the next level is the database level, where you actually create your tables, update these tables with data. I'm considering relational database in this example, but that's when actually, writing SQL scripts to create your database, update it. You are creating your indexes, if it's a stored procedure, you're doing that. If some kind of sequencing you want to create, you do all of that, right? So this is when you're actually doing the creation work, and based on all this modeling and design that you have determined. One example here would be, let's say we have some product customer table, and it's an e-commerce website, and we are storing some kind of information, right, about the product and the customer in this example, orders, stuff like that. So I'll start with like conceptualizing, right? Like, hey, at the bare minimum, I have a customer table and they have a name and number, right? And I have a product table which has a product name, let's say ID, price, and there's a relationship between these two tables, right? Like a customer can buy many products. Products can be sold to customers. Okay, I have conceptualized this, right? So I have two tables with some bare minimum data. Now I will go into the logical modeling, right? Where I'm defining, hey, customer name would always be a string. It will not be an integer, right? Customer number would be an integer. We don't want it to be a name, right? So you just keep on adding constraints as per your business rules, right? Product name would be a string, price would be an integer, right? So you want to like drill down and make it more, apply business logic here and constraints around what data you're collecting and what relationships would exist, right? And then physical level would be, what does your primary key look like, right? What does your foreign key look like? Are there any indexes you are adding? If yes, yes, then like, what are those indexes on all tables, all columns, the index and stuff like that. So now you're thinking about performance, right? So you are like, now like you have your core design and now you're thinking about performance. And then at the final stage, you actually have a database, right? So you have, let's say, customer table, orders table, product table, in this example, product orders, and you're actually seeing, the tables are created and they're populated with some basic data points. So this is basically how data modeling works. You start small and you build on top of it based on your business needs and your technical requirements. And then once you have the design in place, you actually do the creation. And this is when you can say the data modeling or data design is completed. And then, of course, as your business grows, you only build on top of it. You want to maintain, there's some other performance requirements or business needs, you'll always build on top of this. And this process will continue, right? Like if I want to add a new table, then I would want to continue. I want to start with conceptualizing, then doing the logical design, then the physical design, and then actually create a table and populate it. So this will, anytime you do any kind of data modeling, usually you can follow the same process. I'll just quickly show you like a small script I wrote in SQL to create a table and how that table looks like. And usually in a Java microservice, how can you, write a script and, spin up a database. Let me, I'm going to share my IDE. Just let me know when you can see it. One second, I'm still sharing. And yeah. Can you see my IDE?
Yeah.
Okay, thank you. Yeah, so this is my student management application where I'm just like, collecting information about students and their degree information and their advisor years of enrollment, stuff like that. It's a typical Java application. What I have done here is a couple things. So I have created an in-memory H2 database, which basically stores a relational, let me zoom. Yeah, which basically it's an in-memory database. It basically stores relational information because I have decided that for my student management application, my data would be relational. I'm not storing a key value pair. I'm not storing a document or it's not a graph data structure. So I've seen something locally, which is H2 database. And I've written a small script here just to create the table, right? So I'm creating a student table. It has a student ID, which is an integer. It auto increments every time I add a new student. So I don't have to keep on providing the ID and keep a track of the ID or the count of records I have. It's a primary key, right? So it's unique per student. Then I have my first name and last name of student, which can never be null. So these are the constraints that I've defined at the logical level, right? It's a string, which is, or varchar, which is limit 255, which is the highest for varchar. Then I have my date of birth of the student. It's type date. It can never be null. And the years of enrollment. So all this information I want to collect every time a new student is added to my system or to my university, to my class, right? And this is all the information that I want to persist about a student in my system, right? So I've written a small SQL script which will create the table for me. And if I look at the application side, I have, once again, I'm gonna go to the data, yeah. I basically have a model of the student, which is my entity on the business side, and it just tells me, it's just the data access layer, which tells me, hey, for my service, this is how my data looks like, and this is all the information that I'm going to persist in the database, and then all sorts of functions that I have to read and write to my database from the service or application side. And I have a repository which helps me. A lot of this is, like behind the scenes. Spring Framework does it for us, but I have a student repository which allows me to do CRUD operations on the student table. So all this code, thanks to Spring, is already given to me out of the box. And once I run this application, the way this application is structured, it'll automatically read the script, and it will create a table, create a database named student. It will create a table named student, and all of these things will be populated. And since my application is running, I can now actually look at the database, and I've already pre-populated some fields. So if I, can you see my screen? Can you see the browser? Yeah. So basically, I already have an H2 console. I'm able to log into my database from the browser. I already have a student table, as you can see, right? And some other information. Right now, I'm the only user of this database, and then I have student table. And if I just select start from the student, I should be able to. Oh, I need to log in. Log in again, and yeah, I should be able to see all the information that I stored in my table so far. So just writing that script helps me create a table, and then for my application I have APIs, and I'm just like calling those APIs, and I'm able to manipulate my data, right? And in this case, it's a relational database with all sorts of information that I want to process related to a student. So at the application level, if you want to create, like in this example, relational database, is as simple as defining your entities at the data access layer, writing your SQL scripts, and then you should be able to, manipulate your data. I see a question like why a DAO folder is used in a project. What is the purpose? It just helps to structure your project folders properly. You have a controller layer folder, which takes care of all APIs and TTOs. Then you have a service layer, which takes care of business logic. And then you have your, let's say, DAO folder or data access object layer, which helps you define entities and do database operations. So it just helps with structuring your projects or your application. It's just a standard to do that. You don't have to do it, but it's just considered a standard or best practice, or it's just very common to do so. That's why I would say data access object layer or DAO layer, which takes care of, I guess, integration between your service layer and the database. Yeah, and if we have reached the end of the session. Can you see my screen?
Yeah.
Yeah, we have two more. All this recording and all the presentations are on our presentation on our Women Who Code GitHub site, and all these recordings we have done are on our YouTube channel, so do check them out. And we have two more sessions for this year. We have one next week, which is about improving your code debugging skills, and we have one on December 8th, which is about what is Git and some version control systems out there, and what does version control actually mean. And if you're interested in Women Who Code, there are many more events and technical tracks that we do. You can join our mailing list. We have a Backend study group. Slack channel. You can join our Slack workspace and do join our channel. And yeah, if you have any questions or ideas you want, or any topics you want us to cover, you can totally mention that in the Slack channel. And Harini, you can share the resources and the
Yeah,
feedback
I'll
form as
post
well.
them
We have a
now.
feedback form. You can tell us how we did. If you have any topics you want us to cover, share your ideas and we'll get to work.
Yeah, I just posted a bunch of useful links. It has this link to the feedback form and the link to our GitHub repo. And if you're not in our Slack space, it has the link to that as well. And since this session is recorded, this would be posted to our YouTube channel too in the next few days.
Thank you, Lena and Smriti.